On a frigid morning in late January 1944, inside a concrete testing facility 30 kilometers west of Bucharest, Chief Engineer Alexandru Dimitrescu placed a German 75mm artillery shell on the examination table and felt the cold metal through his wool gloves. The shell had failed to detonate during operations on the Eastern Front 3 weeks earlier, one of 47 similar failures reported that month alone. Dimitrescu believed, as did his superiors in the Romanian Ministry of Armaments, that they were dealing with simple manufacturing defects, perhaps hastily produced rounds from overstretched German factories. Within 6 weeks, his testing would reveal something far more profound about the nature of industrial warfare itself. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you are watching from. It really helps support the channel. What these Romanian engineers were about to discover would fundamentally reshape their understanding of why the Axis powers were losing the war. And the answer had nothing to do with courage, tactics, or even numbers of soldiers. It had everything to do with something as mundane as the molecular structure of steel. Alexandru Dimitrescu had spent 23 years working in metallurgy, first at the Reșița Steel Works in western Romania, then at the Royal Arsenal in Bucharest. His hands knew metal the way a pianist knows keys, by touch, by sound, by the subtle resistance it offered to tools. At 47 years old, with wire-rimmed spectacles perpetually sliding down his nose, he ran the most sophisticated materials testing laboratory in Romania. His team of 9 engineers had been tasked with analyzing why German ammunition was experiencing unprecedented failure rates. Standing beside him at the examination table was Ștefan Ionescu, a 29-year-old metallurgist who had studied at the Polytechnic University of Bucharest before the conflict began. Ionescu had sharp eyes and sharper instincts, often noticing patterns that others missed. Together, they had examined hundreds of failed munitions over the past 6 months, documenting fracture patterns, chemical compositions, and manufacturing inconsistencies. The morning light filtered through high windows, casting long shadows across rows of testing equipment, hardness testers, spectrometers, microscopes, and metallographic polishing stations. The air smelled of machine oil and the acrid tang of chemical etchants. In the corner, a German liaison officer named Hauptmann Friedrich Keller stood with his arms crossed, watching the Romanian engineers work. Keller had been sent from Berlin to observe the investigation, and his presence made everyone in the laboratory acutely aware that their findings would be scrutinized at the highest levels. Dimitrescu picked up a jeweler's loupe and examined the shell casing's exterior. The manufacturing marks were crisp, the threading precise. Nothing visible suggested inferior workmanship. He turned to Ionescu and said, "Prepare it for sectioning. I want to see the grain structure of this steel." Ionescu nodded and carefully transported the shell to the cutting station. Using a precision saw, he would slice through the casing to create samples thin enough for microscopic examination. This process would take hours, but it was the only way to understand what was happening inside the metal itself. While Ionescu worked, Dimitrescu walked to a filing cabinet and retrieved a leather-bound logbook. He flipped through pages of data collected over months of testing. The pattern was undeniable. German artillery shells, mortar rounds, and even small arms ammunition were failing at increasing rates. Shells that should have detonated on impact were breaking apart without exploding. Casings were cracking during firing. Fuses were malfunctioning. The failure rate had climbed from approximately 3% in 1942 to nearly 12% by late 1943. Dimitrescu had initially attributed this to wartime production pressures. Germany was producing ammunition at staggering rates, over 8 million artillery shells per month by 1943, along with hundreds of millions of small arms rounds. Surely, he had reasoned, such volume inevitably led to quality compromises. But as he examined the data more closely, he noticed something peculiar. The failures were not random manufacturing defects. They showed consistent patterns suggesting fundamental problems with the steel itself. Hauptmann Keller approached the desk, his boots clicking on the concrete floor. He was a technical officer, not a combat soldier, with a methodical mind suited to logistics and engineering. Keller spoke adequate Romanian, though he preferred German when possible. He said in his native language, "Herr Dimitrescu, have you reached any conclusions?" Dimitrescu responded in German, which he had learned during his university years. "Not yet, Hauptmann. We need to examine the microstructure. The external inspections reveal nothing obvious." Keller's jaw tightened. The Wehrmacht needs answers. These failures are affecting operations across all fronts. The Eastern Front particularly requires reliable ammunition. Dimitrescu understood the subtext. The German armed forces during the war were engaged in a massive conflict spanning thousands of kilometers, consuming ammunition at rates that would have been unimaginable just years earlier. Any systematic failure in munitions was a strategic catastrophe. He said, "We are working as quickly as precision allows, Hauptmann. Metallurgy does not yield its secrets to haste." Keller nodded curtly and returned to his corner, where he lit a cigarette and stared out the window at the winter landscape. 3 days later, on a Thursday morning, everything changed. A Romanian military truck arrived at the testing facility, carrying wooden crates marked with white stars and English text. Dimitrescu met the delivery officer at the loading bay, his breath forming clouds in the cold air. The officer, a captain named Vasile Petrescu, saluted and said, "Chief Engineer, these were captured 3 weeks ago during operations in the Ukraine. American supplies that were being transported to Soviet forces. The ministry thought you might find them useful for comparison." Dimitrescu felt his pulse quicken. American ammunition. He had heard stories about American industrial capacity, factories that operated 24 hours a day, production lines that could manufacture a complete bomber aircraft every 63 minutes, steel mills that poured more metal in a week than some European nations produced in a year. But he had never examined their ammunition firsthand. He directed workers to carry the crates into the laboratory. Once inside, he used a pry bar to open the first crate. Inside, packed in wood shavings and waxed paper, were rows of 75mm artillery shells. The brass casings gleamed even in the laboratory's dim light. Dimitrescu lifted one shell and was immediately struck by its weight. It felt substantial, dense, perfectly balanced. Ionescu joined him, and together they examined the American shell next to a German one of the same caliber. Visually, they were similar, both roughly 60 centimeters long, similar diameter, comparable overall design. But when Dimitrescu placed them side by side on a scale, the American shell weighed approximately 800 grams more than its German counterpart. "Interesting," Ionescu murmured. "The additional weight is not in the explosive payload. I can tell from the balance it must be in the casing itself." Dimitrescu nodded. "Thicker walls, perhaps, or denser metal." "We need to section both shells and compare them directly." Over the following week, the two engineers worked with focused intensity. They cut samples from both American and German shells, polished them to mirror finishes, and etched them with acidic solutions to reveal their crystalline grain structures. What they saw under the microscope left them stunned. The German shell casing showed a microstructure that Dimitrescu recognized immediately. Coarse, irregular grains with visible inclusions of slag and sulfur. The grain boundaries were poorly defined, suggesting inadequate heat treatment. In some areas, he could see actual voids in the metal, tiny cavities where impurities had prevented proper solidification during casting. This was steel that had been produced quickly, without sufficient refining or quality control. The American shell casing was entirely different. Under identical magnification, its microstructure revealed fine, uniform grains with virtually no inclusions. The grain boundaries were crisp and evenly distributed. The steel had been properly heat-treated, carefully alloyed, and meticulously refined. It was, quite simply, superior metal at every level. Dimitrescu leaned back from the microscope and removed his spectacles, rubbing his eyes. Ionescu, who had been examining a parallel sample, looked up with an expression of disbelief. "The Americans are using higher quality steel for their ammunition than we use for precision instruments," Ionescu said quietly. Dimitrescu replaced his spectacles and performed a series of hardness tests, pressing a diamond-tipped indenter into samples of both metals with precisely calibrated force. The American steel measured consistently at 58 on the Rockwell C scale, hard enough to withstand tremendous pressure, yet ductile enough not to shatter. The German steel varied wildly, from 42 to 55 on the same scale, with some samples showing brittleness that suggested improper tempering. He conducted chemical analysis next, using spectrographic equipment to determine the exact composition of each steel. The German samples contained approximately 0.4% carbon, 0.7% manganese, and significant quantities of phosphorus and sulfur, impurities that weakened the metal. The American samples showed precisely controlled alloying, 0.38% carbon, 1.2% manganese, traces of chromium and molybdenum for strength, and phosphorus and sulfur levels below 0.02%, negligible by comparison. The implications were staggering. The Americans were not just producing more ammunition, they were producing fundamentally superior ammunition, with quality control that ensured every single shell met exacting standards. Hauptmann Keller received the preliminary report with visible tension. He read through Dimitrescu's findings twice, his face growing pale. Finally, he said, "This cannot be correct. You are suggesting that American steel is superior to German steel." Dimitrescu chose his words carefully. "I am not making suggestions, Hauptmann. I am reporting measurements. The microstructural evidence is unambiguous. The American shells are manufactured from higher quality steel with better refinement and stricter quality control." Keller stood and paced the laboratory. "Germany has the finest metallurgical tradition in Europe. Krupp steel built the industrial age. How can you claim—" "I am not claiming anything," Dimitrescu interrupted gently. "The metal itself is telling us its history. Look through the microscope yourself." Keller did, spending nearly 30 minutes examining the samples. When he finally stood, his shoulders sagged. He said, "I must report this to Berlin. They will want independent verification." "Of course, Dimitrescu said. "I would expect nothing less." But Dimitrescu already knew what independent verification would show. The evidence was irrefutable. What he did not yet fully understand was why. Why was American steel so superior? And more importantly, why had German steel quality deteriorated so dramatically? The answer came from an unexpected source. Among the captured American supplies was a technical manual, a thick book printed on high-quality paper with clear diagrams and detailed specifications. It was a metallurgical handbook produced by the United States War Department, intended for quality control inspectors at ammunition factories. Dimitrescu spent 3 evenings translating sections of the manual with the help of a colleague who spoke English fluently. What he read astounded him. The Americans had systematized ammunition production to an extent that seemed almost incredible. Every step of the manufacturing process was standardized, measured, and controlled. Steel composition was verified by spectrographic analysis at multiple points during production. Heat treatment followed precise time-temperature protocols. Dimensional tolerances were measured to within thousandths of a centimeter. Samples from every production batch underwent destructive testing before the batch could be shipped. But the most revealing section dealt with raw materials. The manual specified that all steel used in ammunition production must come from furnaces using low-sulfur ore, with scrap metal content limited to less than 15% of the total charge. The steel must be refined through multiple stages, including basic oxygen processing to remove impurities, followed by vacuum degassing to eliminate dissolved gases that could create voids. Every heat of steel, each batch produced by a single furnace charge, received a unique identifier that followed it through the entire manufacturing chain. This level of quality control required enormous resources, sophisticated testing equipment, trained personnel, and most critically, time. Each American shell took approximately 30% longer to manufacture than a German equivalent, but the result was ammunition that virtually never failed. Dimitrescu began to piece together what had happened to German production. In the early years of the conflict, German ammunition had been excellent, well-made, reliable, built according to the rigorous standards of peacetime manufacturing. But as the war expanded and demand skyrocketed, German industry had faced impossible choices. They could maintain quality and produce insufficient quantities, or they could increase production by relaxing standards. They had chosen quantity over quality. Furnaces that had previously been charged with premium ore now accepted whatever materials were available, including high sulfur ore from captured territories. Scrap metal content increased from 15% to over 50% in some batches. Heat treatment times were shortened to increase throughput. Quality control inspections became cursory rather than comprehensive. The result was ammunition that looked adequate externally, but was fundamentally compromised at the molecular level. Ionescu found additional evidence when he examined production markings on the German shells. Each shell bore a stamp indicating which factory and production date it came from. By correlating these markings with failure rates, he discovered a clear pattern. Shells produced before 1942 had failure rates below 2%, while those produced after mid-1943 had failure rates approaching 15%. They sacrificed tomorrow's reliability for today's production numbers, Ionescu said as he showed Dimitrescu the correlation charts. Every shell they produced quickly is now failing in the field. Dimitrescu nodded grimly. He thought about artillery crews on the Eastern Front, loading shells into their guns with decreasing confidence, never knowing if a round would function properly or shatter in the barrel. He thought about the cascading effects, artillery bombardments that failed to neutralize enemy positions because 12% of shells malfunctioned, infantry advances that stalled because supporting fire was unreliable, defensive positions that fell because counter-battery fire was ineffective. The metallurgical failure was becoming a tactical failure, which was becoming a strategic failure. To understand the human impact, Dimitrescu requested and received after-action reports from German artillery units on the Eastern Front. One report, filed by Hauptmann Ernst Weber of an artillery battalion, described an engagement in October 1943 near the Dnieper River. Weber's battery had fired 217 shells during a 6-hour period supporting an infantry counterattack. Of those shells, 29 had failed to detonate, and 7 had shattered in the barrel, temporarily disabling the guns. Weber had written in his report, "The gunners no longer trust the ammunition. They flinch when loading shells, anticipating barrel failures. This hesitation slows our rate of fire and diminishes combat effectiveness. More concerning is the psychological impact. Men who cannot trust their weapons lose confidence in their ability to accomplish their mission." Dimitrescu read these words multiple times. Weber had identified something crucial. The problem was not just mechanical but psychological. Unreliable ammunition eroded the morale and effectiveness of the soldiers who depended on it. By contrast, captured reports from Soviet forces who had received American ammunition through the Lend-Lease program described a completely different experience. One Soviet artillery commander had noted that American shells had a failure rate below 0.5%, so low that gunners simply assumed every shell would function as designed. This confidence translated to faster firing rates, more aggressive tactics, and higher overall effectiveness. The mathematics of industrial warfare became brutally clear. The United States was producing approximately 16 million artillery shells per month by late 1943, compared to Germany's 8 million. But American shells were also significantly more reliable. If German shells failed 12% of the time, while American shells failed only 0.5% of the time, then the effective ammunition ratio was not 2-to-1, but closer to 3-to-1 in America's favor. And this did not account for the additional shells lost when German rounds shattered in gun barrels, damaging the weapons themselves and requiring time-consuming repairs. Dimitrescu calculated that the true effective ammunition advantage was probably closer to 4-to-1 when all factors were considered. He discussed these findings with Ionescu over lunch in the facility's small cafeteria. The younger metallurgist stirred his soup thoughtfully and said, "What strikes me is the philosophy behind it. The Americans built their production system to prioritize long-term reliability, even though it meant slower initial production. The Germans prioritized immediate output, accepting that it would lead to long-term problems. It reveals two completely different approaches to industrial planning." Dimitrescu agreed. It also reveals differences in resources. The Americans could afford to take longer because they had sufficient raw materials and could maintain their supply chains. The Germans were under constant pressure to produce more shells, pressure to make do with inferior materials, pressure to cut corners wherever possible. Do you think they understood what they were doing? Ionescu asked. The German planners, I mean. Did they know they were producing inferior ammunition? Dimitrescu considered the question. I suspect they knew but felt they had no choice. What good are perfect shells if you do not have enough of them? They gambled that quantity would compensate for quality. It was a losing gamble, Ionescu said quietly. The final piece of the puzzle came when Dimitrescu obtained access to German metallurgical specifications from before the conflict began. These documents, dated 1937, showed that German peacetime standards for ammunition steel were actually comparable to current American standards. The Germans had known how to make excellent ammunition. They had simply become unable to maintain those standards under wartime pressures. He found a particularly telling document, a memo from 1942, written by a German metallurgist named Dr. Heinrich Strauss, who had warned his superiors about declining steel quality in ammunition production. Strauss had written, "We are observing increased inclusion content, inconsistent heat treatment, and inadequate quality control in ammunition steel production. If these trends continue, we will face systematic failures in the field within 12 to 18 months. I strongly recommend reducing production targets to allow for proper quality control protocols." The memo had been stamped read and filed, with no indication that its recommendations had been implemented. Dimitrescu could imagine the decision-makers' reasoning. They were fighting a multi-front conflict against enemies who outnumbered them. They needed shells now, not perfect shells later. The short-term imperative had overridden long-term sustainability. By mid-March 1944, Dimitrescu's laboratory had completed comprehensive testing of over 300 German and American shells. His final report ran to 78 pages of detailed analysis, charts, microscope images, and chemical compositions. The conclusions were stark and unambiguous. American ammunition was manufactured from superior steel, produced with better quality control, and designed for long-term reliability. German ammunition showed evidence of declining material quality, shortened production processes, and inadequate quality assurance. The trend was worsening month by month as resource constraints intensified. Hauptmann Keller read the final report in Dimitrescu's office. When he finished, he sat silently for several minutes. Finally, he said, "You understand what this means for the war effort." "I understand that it means industrial capacity matters as much as courage or tactics," Dimitrescu replied. "Perhaps more." Keller nodded slowly. "I will submit this to Berlin. But between us, Engineer Dimitrescu, I doubt it will change anything. The decision-makers will say we must produce more, not less. They will argue that some shells failing is preferable to having no shells at all, and perhaps they are correct. I am not a strategist, but as a technical officer, reading this report fills me with—" He paused, searching for the word, "with a certain pessimism about our industrial prospects." After Keller left, Dimitrescu stood at the window, looking out at the Romanian countryside. He thought about the larger implications of what he had discovered. Modern warfare was not just about soldiers and tactics. It was about furnaces and foundries, about chemical compositions and heat treatment protocols, about quality control systems and raw material supply chains. It was about the unglamorous invisible infrastructure that turned iron ore into functioning weapons. The side that could master that infrastructure, that could maintain quality while scaling production, that could ensure every shell was as reliable as the last, that side held an enormous advantage. Not because their soldiers were braver or their generals more brilliant, but because their industrial system was more robust, more systematic, more sustainable. Ionescu joined him at the window. The younger engineer said, "Do you think the Germans can fix these problems?" Dimitrescu shook his head. To fix them would require reducing production to implement proper quality control. That would mean fewer shells available in the short term. I cannot imagine they will accept that trade-off, not while engaged in active combat on multiple fronts. "So they are trapped," Ionescu observed. "They cannot maintain their current production rate without accepting inferior quality, but they cannot reduce production without losing tactical flexibility." "Exactly," Dimitrescu said. "They are caught between impossible choices, which is perhaps the definition of a losing strategic position. In the months that followed, Dumitrescu's laboratory continued monitoring German ammunition quality. The deterioration continued unabated. By July 1944, failure rates for some production batches exceeded 20%. By October, they approached 25%. The German armed forces during the war were, in effect, fighting with one hand tied behind their back, not because of any lack of courage or tactical skill, but because roughly 1 in 4 shells could not be trusted to function properly. Meanwhile, American ammunition production continued to increase. By mid-1944, the United States was producing nearly 20 million artillery shells per month, all manufactured to exacting standards, with failure rates below 0.6%. The industrial advantage was becoming overwhelming. Dumitrescu sometimes thought about Hauptmann Weber, the artillery officer whose report he had read. He wondered if Weber had survived the conflict and whether he ever learned why his shells kept failing. He suspected Weber had probably attributed the failures to bad luck or inadequate training or sabotage, never imagining that the true cause was something as abstract and invisible as the grain structure of steel. After the conflict ended, Dumitrescu returned to civilian metallurgy, eventually becoming a professor at the Polytechnic University of Bucharest. He occasionally gave lectures about what he called the metallurgy of defeat, how material science and industrial capacity had shaped the outcome of the conflict more profoundly than most people understood. In one lecture, delivered in 1952 to a class of engineering students, he said, "When people ask why the Axis powers were defeated, they usually cite numbers of soldiers, or strategic mistakes, or industrial capacity in general terms. These are all true, but they miss the deeper point. The defeat was decided in the foundries and furnaces, in the quality control laboratories and the material specifications. It was decided by people who understood that a reliable shell is worth more than 3 unreliable ones, that systematic quality is more valuable than momentary quantity, that patience in production yields advantages that haste can never overcome." He would hold up 2 shell casings, one German, one American, both from 1944, and pass them around the classroom. "These look identical," he would say, "but under the microscope they tell completely different stories. One tells a story of compromised standards and desperate shortcuts. The other tells a story of systematic excellence and sustainable production. In modern warfare, that difference is decisive." Ionescu, who had remained friends with Dumitrescu after the conflict, occasionally joined him for these lectures. The 2 engineers would discuss their wartime discoveries, marveling at how something as seemingly mundane as steel grain structure had illuminated such profound strategic truths. "We were looking at ammunition," Ionescu once reflected, "but we were really witnessing the triumph of systematic thinking over improvisation, of patience over urgency, of industrial discipline over desperate expedients." Dumitrescu agreed. He sometimes wondered what would have happened if German decision-makers had read Dr. Strauss's memo differently in 1942, if they had reduced production targets, implemented rigorous quality controls, and accepted short-term scarcity for long-term reliability. Would it have changed the war's outcome? Probably not, he concluded. The resource advantages enjoyed by the Allied powers were too vast. But it might have reduced the rate of deterioration, might have prolonged German tactical effectiveness, might have prevented some of the catastrophic failures that occurred in the conflict's final years. The real lesson, Dumitrescu believed, was about the nature of industrial competition. In peacetime, companies that cut corners to reduce costs might gain short-term market advantages, but they would eventually be overtaken by competitors who maintained quality and built sustainable systems. War simply compressed this process, making the consequences visible within months instead of years. The Americans had understood something fundamental. In a prolonged industrial conflict, sustainable quality always defeats unsustainable quantity. You could produce shells quickly by accepting inferior materials and relaxed standards, but those shells would fail in the field, eroding tactical effectiveness and ultimately wasting the resources used to manufacture them. Better to produce fewer shells that all function correctly than more shells of which many are worthless. This principle extended beyond ammunition to virtually every aspect of industrial warfare. Aircraft engines, vehicle transmissions, optical equipment, electronic components. Everywhere the pattern repeated. American industry prioritized systematic quality, while Axis industry increasingly resorted to corner-cutting and expedience. Dumitrescu's archive, preserved at the Polytechnic University, contains thousands of pages of test results, metallographic images, and analytical reports from those crucial months in 1944 when he examined German and American ammunition. Researchers who study these documents today are often struck by how thoroughly the metallurgical evidence predicted strategic outcomes. The grain structure of steel crystals, invisible to the naked eye, told the story of industrial systems under stress, of competing manufacturing philosophies, of the ultimate triumph of sustainability over expediency. In his later years, Dumitrescu would sometimes take out one of the American shells he had saved from the original captured shipment. He would hold it in his hands, feeling its weight, admiring the precision of its manufacture. Somewhere in the American Midwest, he would think, workers in a vast factory had produced this shell according to rigorous specifications, never cutting corners, never accepting good enough, always maintaining standards even when under pressure to produce more. Those workers had probably never thought of themselves as warriors, but in a very real sense, they had been fighting the conflict as surely as any soldier on the front lines. They had been fighting with metallurgical excellence, with quality control protocols, with systematic precision. And they had won, not through dramatic action or heroic sacrifice, but through the unglamorous discipline of making every single shell correctly, one after another, month after month, until the sheer accumulated reliability became an overwhelming advantage. That, Dumitrescu came to believe, was the true nature of modern industrial conflict. Victory belonged not to the side that could produce the most in the shortest time, but to the side that could maintain excellence while scaling production, that could be both fast and thorough, both prolific and precise. It belonged to the side that understood that quality was not a luxury to be sacrificed under pressure, but a strategic necessity that determined outcomes. The molecular structure of steel had revealed all of this, if you knew how to read it. And in a testing facility west of Bucharest in early 1944, Alexandru Dumitrescu and Ștefan Ionescu had learned to read it very well indeed. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Do not forget to subscribe for more untold stories from World War II, and check out the video on screen for another incredible tale from history. Until next time.